Hello mathematicians, we're now going to have a look at what are called the geometrical properties of the parabola. Now this first one you've come across already, and that is about focal chords and intersection of tangents. And we have that a chord that joins 2 points on a parabola is a focal chord if and only if the tangents at the endpoints of the chord meet on the directrix. So we've come across that fact before. So here we have our 2 points on the parabola. We have a chord joining them. It's passing through the focus. And when we look at these two tangents, they're actually meeting on the directrix. But even more than this statement here, we saw before that the product of the gradients of these two tangents, PQ was how we saw it, equals -1, which implies that these two are perpendicular as well. So it's good to know that property, but it's not so much a matter of recalling that property as being able to do the sort of analysis necessary to prove that property. This point here, same sort of thing, focal chords and intersection of tangents. A chord joining 2 points on a parabola is a focal chord if and only if the tangents of the endpoints meet on the directrix. So this is sort of classic geometry. We've got a statement and we've got what's called its corollary, which is it's the same statement represented in a different logical line. So up here we were saying that if we have a focal chord, the endpoints meet on the directrix. Down here we're saying if the endpoints meet on the directrix, then we have a focal chord. Neither of those, again, mentions that fact that we know that this is a right angle. So let's just reconvince ourselves of this point using GeoGebra. Here we can see we have our 2 points, they're passing through the focus. As you see, if I change the value of A, it changes the focus and the width of the parabola, if you like. And if I move these points around, so if I move P down, then what I notice is that once I'm not passing through the focus, those two tangents don't intersect on the directrix, and the angle is no longer 90 degrees. But when I move the points so that that's the case, and this will just be a little bit touchy, so there we're passing through the focus, or close enough to it there, and we've got an angle of 90 degrees. So I move this one and just move this again so that we're passing through the focus, then we're just reinforcing that point. So I can't quite get it on the focus. But in here, we've got an angle of, again, 90 degrees if we pass through the focus. And we're cutting on the directrix. So let's now have a look at another property, the only other one that we really pay any attention to, and it's the reflection property. Now what the reflection property says is something that you might have come across in junior science, or physics students might have come across it, and that is if we send beams in which are parallel to the axis of the parabola, when they are reflected from the parabola, they all pass through the focus. So this is the basis of operation of both receivers and transmitters, and optical telescopes, radio telescopes, and so on. So there's a very practical application of this reflection property, and there's a similar reflection property for circles, ellipses, and so on, but we're just looking at it for the parabola at the moment. So the reflection property, when we look at it mathematically, says that the interval joining and interval is just a fancy word for line, the line joining a point on the parabola to the focus. So here's a line joining a point on the parabola to the focus, this line here, and the line through the point parallel to the axis, so that's this line here, so that line is parallel to the axis. So these two lines are equally inclined to the tangent at the point. So these two angles are the same. Now, in real science, if you like, they tend to look at these angles and talk about angle of incidence and angle of reflection, but we're not worried about that. So it's the angles between this beam from point to the focus and from that point parallel to the axis, and we want the angles in here, just there and there, to be the same. So we're going to have a look at a quick proof of that. Again, it's not a proof to be memorized, but the shape of the proof, in a sense, needs to be memorized. So here's a diagram with a little bit less complication on it, and in fact I'll just try and rub those lines off. So what we can see is that if we mark the angles SKP, so SKP, this angle here, and QPB, so this angle up here, so this angle and this angle, they're corresponding angles on parallel lines, being the y-axis and the line that we've put in there. So they're equal to each other. So if SK equals SP, so don't know whether you can see that, but it's showing this line here in red and this line here. If we can prove that those two equal each other, then triangle KSP will be isosceles, and if it's isosceles, then we know that the base angles are equal, so this one and this one will be equal, and that means that this one over here, which also equals this, gives us these two being equal. So that's the structure of our proof. So in essence, once we know that structure of the proof, our task is really to prove that SK equals SQ. So we do that with simply the distance formula. So SP squared is the distance formula, and I'm using the squared version of it. So that's 2AP back to the x value of 0, so the difference in the x is squared and the difference in the y is squared, and that will then simplify to a squared outside of p squared plus 1 squared. You should convince yourself of that. Just brush up your algebra. And since the tangent has equation px minus ap squared, that means that the coordinates of k, where we cut the y-axis, are obtained by putting x equal to 0. So y is minus ap squared. So then the distance from s to k is simply a plus ap squared, and because we're squaring it, then it's all squared. So what we've shown is that sk equals sp, therefore that's what we're required to show that we have an isosceles triangle, and therefore that those two angles of inclination are equal to each other. So let's have a look at a typical question. So reading it carefully, we'll then try and draw the diagram. So we've got P, so this is a variable point on the parabola, where T is not equal to 0. So it's not talking about the vertex in this case. The normal at P meets the axis of the parabola at N, and PB is the perpendicular from P to the axis of the parabola. Bn is called the subnormal. That's not something that we need to know about, but this is practice in problem solving. So the interval Bn is the subnormal corresponding to P. So let's put that into a diagram. So here's my wonky attempt at a diagram. So we've got our parabola, x squared equals 4ay, our point on the parabola. We've got the normal just here, so I've attempted to draw in the tangent. There's our normal perpendicular to it. It's meeting the axis of the parabola at N. PB is the perpendicular from P to the axis of the parabola, and then this interval is called, as we said, for whatever reason, the subnormal. Part A is a stock question. Show that the normal at P has equation that. So in the interests of brevity here, I'm going to start with the fact that the gradient of the tangent equals the value of the parameter. So we've seen that before. If this was an exam, I would prove that. Then equation of a straight line, y minus y1 equals m. So this is the gradient of the normal outside of x minus x1. Multiply through both sides by t, every term. Gather terms together, and we can see that we get the equation we're meant to, the equation of the normal. Now, For subsequent parts, part B says write down the coordinates of B and N. And looking ahead, we can see it says, hence prove the length of the subnormal, so that's just the distance Bn, is constant, independent of where P is on the parabola. Now at the moment we may have no clue what that actually means or will entail. So part of our problem solving technique is to do what we can and then just keep reassessing our progress. So we know that we'll be able to write down the coordinates of B and N. So that should be step number one, and see where we go. It's going to be, if it was an exam question, marks in any case. So to get the coordinates of N, so at N, we know that the value of x equals 0. It's where we cut the y-axis. Therefore, from our equation for the normal here, when we put x equals 0, we've got ty equals 2at plus at cubed. We divide through by t to get the coordinates of y. Therefore, we can see that the coordinates of n are going to be 0 and 2a plus at squared. Now, for b, at b, x equals 0 as well, but the y value, because this is a line which is perpendicular from P to the axis, it's going to have the same y value as P. So the coordinates of P are going to be 0 and at squared. Now, we then revisit part C. It says, hence prove the length of the subnormal is constant, blah, blah, blah. Again, we may not have picked up on it yet, so we just do what we can. We know how to find the length of an interval. So if we find the length of Bn, or Nb, doesn't matter. Sometimes I use this little notation, two little, I don't know what you call them, those little bracket signs up above, as shorthand for length of Bn, but we could use the English if we wish to. So how do we get the length of Bn? Well, because it's on that vertical line, the axis, it's just the difference in the two y values. So we're going from a y value of 2a plus at squared, and we're going down to at squared, so that gives us 2a. And at that point, hopefully the penny drops, because what we see is that the length of the subnormal is a constant, and its value is equal to 2a, where we know that a is just the focal length of the parabola. So it doesn't matter where point P is, then the value of Bn is always going to be 2a, because there's no P or T or any other variable that turns up in there. So this is a good example of just going ahead with problem solving, using what we know and seeing where it takes us. So if you apply that sort of logic to these questions, have a go.